Hello everyone, I'm Neil. Here I want to talk about the HyperDbg. So the HyperDbg is an open source, community-driven, hypervisor-assisted user mode and kernel mode Windows debugger with a focus on using model hardware technologies. It is a debugger designed for analyzing, fusing, and reversing. Debuggers are indispensable tools in software development. Developers use them to improve software efficiency and security. However, although most of the current debuggers use the latest technology to make themselves more invisible, they do not have rich debugging functions. But HyperDbg solves this problem well. It avoids using operating system APIs and software debugging mechanisms. Instead, it uses the second layer page table, also known as extend page tables, to monitor kernel and user execution. So this picture is a top-level diagram showing how HyperDbg works. Because HyperDbg avoids using the debugging API that comes with the operating system, it is very convenient. In the experiment, 13 packers and protectors are used to detect HyperDbg. However, none of them can detect it successfully. On average, other debuggers have a 44% probability of being detected. Experiment shows that HyperDbg can detect 22% and 26% more malware than WinDbg and x64 debugger. For high-performance debugging, HyperDbg uses a high-performance script engine compatible with VMX root, which is much better than other debuggers. Next, I want to talk about the debugger technical background to let you know it more. So the debugger has four parts. The first is user mode debugger. It mainly includes x64 debugger, OLE debugger, and immunity debugger. The user mode debugger provides a convenient and isolated environment for users. And the kernel mode debugger have WinDbg and JDB. As we all know, in the operating system, the kernel mode has higher permissions than the user mode and can modify more information. Therefore, the kernel mode debugger has higher permissions in accessing registers and memory. It's widely used in reverse engineering and malware analysis. With the progress of malware escape technologies, developers are more interested in more transparent debuggers, and they will not make significant changes to the execution process. And the Intel virtualization technology, which is VTX, it introduced new data structures and to ISA, the instruction set architecture. This technology enables the cores of multi-core CPU to run like several independent processors, enabling multiple operating systems on the same CPU to run simultaneously. And Intel VTX technology has a hardware-assisted memory management unit and a second-level address translation implementation, namely an extend page table (EPT). By converting the guest physical address to the host physical address and the CPU level, EPT eliminates the overhead associated with the software management shadow page table in Intel's design. Each CPU core can use a separate EPT table, which allows multiple independent access concurrency from different operating systems. That's all. Thank you.
Hello, I'll introduce the high-level overview and the back-end architecture of HyperDbg. About the high-level overview, I will talk about the debugging flow, the debugger's event-triggered interface, and its operating modes. And about its back-end architecture, I will talk about its stepping and hooking subsystem and its memory access in VMX root mode. So let's talk about the high-level overview first. The first part is the debugging flow of HyperDbg, and it contains 4 parts. Firstly, the debugging host site functionality provides user CLI as well as this assembler and script engine from the end. Then VMX root mode compatible debugging facilities in the guest are activated through event-based mechanism. Next, the subsystem uses hardware-based features such as extended page tables to execute their operations. Finally, the subsystem receives command from host side. The backend scripting engine does the translation and executing in kernel mode or user mode. And the second part is the debugger's event-triggered interface. So to facilitate the debugging routines, the usage of the underlying functions and building blocks is controlled by an abstracted concept, which referred as an event in the debugger. Subsequently, conditions and actions are defined and used in the subsystem procedures for debugging. An event is the occurrence of an incident that is of interest to the debugger. This comprises a wide range of activities ranging from a specific system called the debugger is set to the monitor to access to a particular memory address. And about actions, upon having an event triggered, the debugger can invoke specific functionalities known as actions. The debugger provides 3 types of action, and they perform differently. They are brick, script, and custom codes. So finally, conditions are defined by the user with logical expressions to constrain the execution of events. And the last part is the debugger's operating mode. So there are 3 modes, and the first one is a VMI mode. This mode allows scripts and custom codes in both user mode and kernel mode for local or remote debugging. And the second one is debugger mode. So this is a powerful operating mode that allows connection to the kernel and halting the system to step in and step over through the kernel and user instructions. So the third one is the transparent mode. Both the 2 modes above can be used in this transparent mode, and it can increase the concealment of the debugger. Then let's turn to the debugger's backend architecture. The first part is its stepping subsystem. In conventional step-in mechanism, it will set rflag trap flag to stop the system after a particular operation. which makes it easier for the debugger to read and write the contents of registers and memory after such operation. However, conventional stepping mechanisms cannot guarantee a line-by-line stepping procedure, as all other CPU cores and processes may execute their routines, and interrupts can greatly alter a program's execution flow. So, as shown in this figure, the operation push RBX is set with flag, and after this operation is performed, the process is halted, but another process or thread is still running. After another thread calls XOR RDI, the content of RDI is changed, and the final output will be wrong. But HyperDbg solves this problem. It uses monitor trap flag to implement the step-in mechanism. And this method belongs to non-maskable interrupts, which makes the operation must be completed on one core while the other core will be halted. Thus, the problem is resolved. And the debugger also has a step-over mechanism, which is similar to conventional step-in mechanism. But the length of the calling instruction will be sent to the debugger. And since other threads or cores may also trigger hardware debug registers, HyperDbg will ignore debug breakpoint exceptions from other process or thread IDs. So the second part is the hooking subsystem. Hooking in the context of debugging is the action of intercepting an arbitrary event, running specific commands, and turning the execution flow back to the conventional routine and at the entry point of the event. However, the problem is that the existing hooking system implement direct memory access, which user mode software can easily check and detect. So to solve this problem, HyperDbg implements hooking functionality by triggering an undefined opcode exception and checking for the originating cause of the exception. And the user can execute arbitrary scripts and set hooks for arbitrary system calls through OS or any return of the execution flow from a system call. And during a user to kernel or kernel to user emulation, the debugger can monitor, execute, or modify the system context before the actual execution of the instructions. And this is implemented by allowing the user to monitor and manipulate memory accesses while remaining transparent by providing two EPT hooking mechanisms that reveal an unmodified version of the target page to the application. Lastly, for hypervisor level debuggers, it is quite challenging to access memory safely because it may lead to system halt or exception, such as access pages out of limitation. And to solve this problem, HyperDbg checks the validity of the page to prevent access to invalid pages. And the debugger uses the Intel TSX, which can help an exception or error without switching between user mode and kernel mode. The debugger uses this ability to determine whether the operation on the target address was successfully executed to check whether the page is valid. So that's on my part. Thank you.
Hello everyone, I'm Isaac and I'm going to show you how to use the HyperDbg to listen to a specific operating system function. So let's first open the HyperDbg software, and we are using the local debugging mode. we should load VMN to initialize the software. So now we can use help output command to show how many ways we can output our result. So we can see here we can output the result to a text file, and then we can output it to a specific IP address. And third is to output it to a named type. And today we are going to use the first two methods. So let's first output it to a text file. I want this text file on my desktop, so I copy the path output. And next we want to output it to a specific IP address, which is our host machine. So before that, we should look at our host machine listener process. This is our code. So we first define a port number and a local address, the IP address. For this IP address, we should go to CMD and use the ipconfig command to see what is our IP address. So you can see here our IPv4 address is 10.33.147.177. So we copy this number to our script, and we start a server, start to listen to our customer machine. And every time it receives a message, it will encoding it and write it to the console. So let's start this process. And now we can go to our customer machine to connect to our host machine. I name 2. And we want to listen to a specific IP address with a port number. And now we can use output command to show how many ways we can output our result. You can see there are two, so but they are not open, so we should use output open command to open these two methods. Now they are open, and we can input our simple script to listen to a system command, and we want to listen to a syscall function. For example, we want to listen to a syscall function, and every time the operating system uses a syscall, the HyperDbg will catch it and do something defining the script. So here we want to know what is content in our registers. So for example, we want to know what content in our RX registers, for example, and we want it output to a text file and to our host machine. So now we should see our host machine is receiving this message, and let's look at the process. As you can see, the encoding part has some problem, but we are receiving something here. But the text file should be okay. So now let's close the software and look at the output text file, and we can see here is every time the system calls the syscall function and what is in our RAX register. Okay, so that's all for my presentation. Thank you.